Good morning. Happy Saturday. This is our morning briefing at the 229th meeting of the American Astronomical Society here at the Gaylord Texan in Grapevine, Texas. Unusual for us to have a regular meeting day on a Saturday, but thanks to the New Year's holiday, that's where we are. I'm Rick Fienberg. I'm the AAS press officer, and I'm assisted this morning by my two deputies. Inga Heyer is monitoring our webcast in the back, and she'll relay questions from our off-site journalists. And Larry Marshall will be handling the microphone during the Q&A after the presentations. Please remember to silence your phones and pagers and beepers and other things. We have 4 presentations, 5 presenters, and 6 press releases going out on the AAS press list in the next few minutes. So when you get back to your computers, you'll have a full inbox thanks to yours truly, the human spam bot. So in case this is your first briefing at a AAS meeting, the way it works is I will introduce the speakers who will then go in order from one to the next, from left to right, and then at the end we'll do questions, and we'll do questions both from here in the room and from our webcast. Well, this briefing is a little bit of an astronomical potpourri. We have black holes, green galaxies, old stars, and results from NuSTAR, which is a high-energy X-ray mission. We're going to hear 4 different sets of results that are being presented here at the meeting. First is going to be John Debes from the Space Telescope Science Institute, who's going to talk about pushing the limits of high contrast with the Hubble Space Telescope. Then, in the third tag team of our press program this week, Eadie Annuar from Durham University in the UK and Peter Boorman of the University of Southampton, also in the UK, will be talking about 2 concealed black holes lurking in our cosmic backyard, unveiled by NuSTAR, one of NASA's X-ray telescopes. They'll be followed by Gwendolyn Eadie from McMaster University in Canada, who will tell us the mass of the Milky Way as measured from globular cluster kinematics. And finally, Matt Malkan from the University of California, Los Angeles, my hometown, will talk about the universe going green, extraordinarily strong oxygen emission in high-redshift dwarf galaxies. And with that, I will turn it over to John. And your PowerPoint did show up, so we're good.
All right, thanks a lot, Rick. I really appreciate it. And I wanted to give a thank you to Ray Villard and Zolt LeVay, who are in the audience here. They helped put this together along with the other public outreach team at Space Telescope, and they did a good job. So if I look good, it's partially because they did a really nice job over the holiday. Okay, so I'm going to talk to you a little bit about a new result that the Hubble Space Telescope has gotten. This is in an accepted publication that will come out in the Space Telescope press release. And it's using an old instrument on Hubble called STIS. STIS, it has the best coronagraphic capabilities that 1985 could design. STIS has been on Hubble for about 20 years, and it was designed in the 80s. And so at that time, coronography or high contrast imaging for faint objects around bright objects was rather primitive, especially in space. And so what you see here is the actual focal plane of the STIS instrument. And you see these wedges and bars, which what you would do is at one of these dots, you will place the star to block out the light. And that's how you do coronography in space. So for the longest time, there was this other narrow occulter called bar 5. It's much narrower than all the other coronographic positions, but it's been left alone primarily because it was damaged during construction of the instrument. But a couple of years ago, Andras Gaspar and Glenn Schneider of the University of Arizona proved that you could actually do high contrast imaging with bar 5, this narrow little bent finger, through an outsourced calibration program. So my talk this afternoon is focused primarily on how you do very high contrast imaging similar to what's being done on the ground with extreme adaptive optics. So what I'm talking about now is some of the observations that I took as part of a general observer program with HST, looking at the protoplanetary disk around TW Hydra. This is a solar-type star. It's about 70% the mass of the sun. It's very young. It's less than 10 million years old. And it's pretty close by as young stars go. So we have a really good window, a bird's eye view of planet formation that's going on in this disk. The image that I'm showing here is actually from an earlier data set from ALMA, which shows that it has a complex series of rings and gaps, which we think is due to active planet formation in this protoplanetary disk. And there's and they all have, all these gaps are within 80 astronomical units, which is an astronomical unit is the Earth-Sun distance. Of particular interest, if you look in this inset here, you see a gap that's in the very inner parts of the system, and that's at about 1 AU, which is the Earth-Sun distance. So this is a really interesting system, and I'll talk about that gap later. But now on to the actual STIS data. So that image I showed before was at millimeter wavelengths, so that probes the thermal emission from the dust in this dust and gas disk. But for scattered light imaging in the visible, which is what STIS can do, we're actually looking at the surface layers of the disk itself. So this was an image of TW Hydra that was taken in 2000. This has been a very heavily studied disk at many different wavelengths, and so this had been observed with Hubble 15, 16 years ago with one of the other coronagraphic locations for STIS. But if we look at what bar 5 can give you, it gives you more angular coverage for less orbits, and you get closer to the star. So in 2016, this is what we can see of the disk now. We get much closer in. The other thing you can notice is that the disk is not evenly bright as a function of angle. On the lower right-hand side, or my lower right, I guess, your lower right as well, it's a little bit brighter, and at sort of 11 o'clock, it's a little bit dimmer. And so this had been seen in 2000, but it was assumed to be a geometric effect and not anything that would change with time. But when I looked in 2015 and 2016 at this disk, I noticed that this feature is actually moving with time at a rate of about 20 degrees per year. This is extremely unusual. We don't, especially because this feature moves in a coherent fashion from about 50 AU all the way out to 140 AU. So this is not a structure in the disk that would be moving with a Keplerian velocity. This is something that's coming from maybe closer into the star. And so what the challenge is to understand what this strange feature that's rotating at 20 degrees per year actually is. Luckily, there's a lot of archival data from Hubble, and there was another instrument on Hubble called NICMOS that observed this disk a couple of times over the intervening years, and so we were able to use a few epochs of NICMOS data and all the epochs of STIS data to confirm this is a circular motion with a period of about 16 years. And this is a much shorter period than you would expect for these distances. So what do we think is happening? Okay, this is just a little cartoon, and it may not be right, but this is what we think is the most plausible explanation for this behavior. We think this asymmetry that we see, this dark and light feature, is due to a shadow in the disk, and that's caused by some part of the inner part of the disk that's shadowing the outer parts of the disk. So one plausible explanation for a structure that shadows the outer parts is maybe a misaligned disk that's being torqued out of the plane of the disk by a companion, like a planet. So if you have that planet that's torquing it and moving it around in a period of 16 years, and you think about where are the most likely positions for a planet, you go back to that ALMA data and you see that gap at 1 AU. Because if the period of 16 years means that it has to be within 6 AU from the star to be orbiting with a Keplerian velocity. So the most likely culprit is a planet within that 1 AU gap. And if you do a calculation, you find that a Jupiter mass planet at 1 AU can torque a disk and make it precess with a period of 16 years. So that's what we think is happening. So why is this unique? So on the left-hand side, or on my left here, we have a visualization that I made based on the data that predicts where the location of the shadow would be as a function of time from 1998 to 2029, 2 full revolutions of this shadow. So it just gives you an idea of what we might see if we could take a snapshot of the disk every couple of months over the next 32 years. But what's unique about this is that this is sort of the first time we've seen a coherent shadow moving with this kind of a period and have had enough epochs to really capture the motion. So this gives us hope that we can use scattered light imaging to probe structures at the very inner regions of these disks. And then one other thing I want to mention is that this is possible because Hubble has been up for so many years, and in particular the STIS instrument has been up for almost 20 years. And having the same instrument taking the same measurements really gives us confidence in our result. So with that, I'll thank my co-authors and leave my contact info up there. Thank you.
Hi everyone, I'm Peter Boorman from the University of Southampton in the UK, and I'm here to talk to you today about local supermassive black hole, or one of two local supermassive black holes that have been uncovered by NuSTAR, NASA's high-energy X-ray mission. So just for a bit of background, if we think about the idea that all large galaxies in the local universe are believed to host a supermassive black hole at its center. Now, these supermassive black holes are the densest objects known in the universe, and as such are great laboratories for studying some of the most extreme physics that you can study throughout the universe. In addition, they're also the most efficient methods for converting mass to energy of any other physical process known. And so they're very, very interesting. But because they've got such a strong gravitational pull, it's now believed that most actively accreting supermassive black holes are obscured. And so to be able to study these hidden monsters that you can see in the bottom right here, you have to be able to study the obscuration that surrounds it. So if we think about this, this video shows a basic sort of simulation of what the obscuration may look like. It looks very beautiful, but this is a computational nightmare to be able to study and model. And so to be able to study the bright intrinsic accretion disk and bright object in the center, it's likely very, very difficult to properly model this obscuring structure that's believed to be a donut structure, but is likely more dynamic than that. So if we think about here, I'm showing a typical spectrum of a heavily obscured black hole that's actively accreting. And the orange region shows the energy that they're most sensitive for previous X-ray satellites. And as you can see, previous X-ray satellites are able to detect this stereotypical feature of iron that's seen in active galactic nuclei spectra. You can't, if you think about obscuration, if a supermassive black hole is heavily obscured, only the higher energy X-rays will be able to penetrate through that gas and dust and reach us. So to be able to really tell that something is heavily obscured, you need to be able to detect these photons here at the higher energies shown on the x-axis here. But these aren't being picked up by the previous X-ray satellites. And so this is where NuSTAR comes in. NuSTAR is very, very useful for this because its optimum energy range includes not only this iron feature, which is a proxy for obscuration, but it also includes the higher energy X-rays that you can pick up. So you can really characterize and classify these obscured sources, and you're able to determine how obscured they are, which is very, very important. So if we go to an example, this is the source I've been working on. It's called IC3639. And it's hosted, the supermassive black hole at the center is hosted by an almost perfectly face-on spiral galaxy in the local universe. The X-ray emission that was detected by NuSTAR is shown overplotted in purple. And it's around 170 million light years away. And just to put that into perspective, our closest galaxy outside of the Milky Way is Andromeda, which is around 2.5 million light years. So it's around 70 times that distance. This is the reference to the paper if you'd like to read up a bit more after the press briefing. And just very, very brief key results for IC3639. In particular, it showed a very, very strong ion line, which is more or less unprecedented amongst other heavily obscured active galactic nuclei in the local universe. So this plot here shows the number of number of heavily obscured confirmed supermassive black holes in the local universe and the strength of their ion line on the x-axis. And so as you can see, the stronger strengths are around 3, and there's only one other AGN with an ion line strength as strong as IC3639, as shown from this plot. And this also shows NGC 1448, which I'll now hand over to Eadie to tell you a bit more about.
Okay, hi, I'm Eadie Annuar. I'm a PhD student at Durham University, UK, and I'm going to tell you about the other supermassive black hole that's discovered by NuSTAR as being hidden from our direct view. This research is presented in Annuar et al. 2017, so if you're interested to learn more about the findings, you can find the full paper in the archive, which was made available several days ago. So this black hole is located in an edge-on spiral galaxy called NGC 1448. The image here shows you the optical image of the galaxy with the NuSTAR X-ray emission detected by NuSTAR layered on top in purple color. The galaxy is located in the southern hemisphere in the Horologium constellation. It is located at a distance of 38 million light years away from us. So if we were going to simply scale down the size of the current universe into the size of the Earth, this galaxy will be located about 30 miles away from us. So it's not exactly at our cosmic backyard, as the title states, but it's still a short drive away. So the fact that the presence of an active galactic nuclei the presence of an accreting supermassive black hole in the galaxy was only discovered about 8 years ago. In astronomy terms, is quite recent. So the fact that this is very close by to us, and yet the presence of a supermassive black hole in the galaxy was only discovered about 8 years ago is quite surprising. As a follow-up to this discovery, we observe the supermassive black holes across multi-wavelength view in the optical using the ESO New Technology Telescope, which is located in Chile, in mid-infrared continuum using the Gemini South Telescope, also located in Chile, in soft X-rays and hard X-ray wavelengths using the Chandra and NuSTAR telescopes respectively. And as you can see from these images, so these observations provide us with the first view of this black hole in these respective wavelengths. So the discovery of this supermassive black hole in 2009 was discovered using mid-infrared spectroscopy, but we provide the first direct imaging of this black hole, particularly in the X-rays and mid-infrared continuum bands. As you can see from this plot, the active supermassive black hole in this galaxy really stands out in the hard X-ray and mid-infrared continuum bands, which is captured by NuSTAR and Gemini South telescopes, respectively. However, in order to measure the amount of gas and dust that surrounds the black hole, we need to perform X-ray spectroscopy, as it is the only way to provide us with the direct measurements of these gas and dust densities. So we perform a broadband X-ray spectroscopy on the black hole emission using the Chandra and NuSTAR data, and we found that the black hole is hidden from us by a very thick cloud of gas and dust. So in these slides here, I'm showing you a brief comparison of IC3639 and NGC 1448 as compared to other heavily obscured supermassive black hole in the local universe. As you can see, NGC 1448 at the bottom there in red color is not only one of the closest supermassive black hole in our universe, but it is also one of the faintest heavily obscured supermassive black holes known to date. So this demonstrates NuSTAR capabilities of finding faint, heavily obscured supermassive black holes in our universe. So what do we learn from these two, the discoveries of these two hidden supermassive black holes in our local universe, along with many other similar NuSTAR studies, is that NuSTAR is helping us to uncover many hidden black holes in the universe, and IC 3639 and NGC 1448 are just two examples of these discoveries made by NuSTAR in our local universe. And the discovery of NGC 1448 as a faint, heavily obscured black hole relatively close to us not only demonstrates NuSTAR capabilities of finding hidden supermassive black hole, but also its ability to find those that are intrinsically faint that are missed by previous hard X-ray observatories. So these discoveries of two supermassive black holes are hiding in our cosmic backyard, especially NGC 1448, in which the supermassive black hole in the galaxy was discovered less than a decade ago, even though it's very close to us, really calls out the question of how many other supermassive black holes out there that were still missing even in our very nearby universe. So with that, thank you for listening.
Hey, hi everyone. Thank you, Rick, very much for inviting me to do this press conference. So my collaborators and my supervisors' names are up there as well, and I'd also like to acknowledge NSERC, which helped funded this research. So before I go ahead with my talk, I just want to create a picture in your head about what the Milky Way galaxy looks like, or what we think it looks like. There tends to be a bulge of stars and gas, and then a disk as well. And then around that, there's a stellar halo, where there's stars and globular clusters. And then we think that the entire galaxy also sits within this dark matter halo, which we can't see. So with that picture in your mind, I'm going to show you my abstract. So this is actually a word cloud I generated from abstracts that I've submitted to conferences and workshops over the past years during my PhD. And it actually sums up pretty well what my research is about. I'm trying to measure the mass and the mass profile of the dark matter halo of the Milky Way. And the way that we're doing this is to use these objects called globular clusters, which are really dense, compact objects of stars. Because around the galaxy, there's a bunch of these globular clusters. And we can go out and we can measure how far away they are from the center of the galaxy, and also how fast they're going. And so with that information about their orbits, we can then infer how much gravitational pull they're feeling, and thus infer how much mass there is in the galaxy. And this is handy because in reality, we can't see that dark matter halo, but we can see the globular clusters. Okay. So here's another cartoon model of the galaxy. There's the disk of the Milky Way. The little red dot is approximately the position of the sun. And so imagine now that we're sitting at the center of the galaxy and we're looking out at one of these globular clusters. If we were to measure its velocity, you'd measure a velocity that's in your line of sight. Okay? But you'd also be able to measure a velocity that's on the plane of the sky, and that would make up the whole speed of the globular cluster. And this is what we call in a galactocentric frame, because this is as if we're sitting at the center of the galaxy. But we're not at the center of the galaxy, we are at the sun. And so when we go out and measure these objects, we're measuring them from a different perspective. We measure our line of sight and the motion on the plane of the sky, which we call a proper motion. And so we need to transform from our perspective to the center of the galaxy perspective, because the math is much simpler if you're sitting at the center of the galaxy. And we know how to do this transformation. Luckily, I can stand on the shoulders of giants here and do this transformation, but you can't do it when you don't have a proper motion measurement of the globular cluster. And we don't have measurements for roughly half of them. So this makes the problem difficult. Okay, so this is just one of the challenges that we come across when we're trying to measure the mass of the galaxy, because you have this mixture of incomplete and complete data. And what people have done in the past is they'll either say, okay, we'll just use the complete data and ignore the data that we have on the left, or they'll throw away the proper motions that we do have and only use those line of sight velocities. And in either case, you're throwing away some of the information that we know. So that's one challenge. Another challenge is that because of this incomplete data, we don't know the average type of orbits that these globular clusters have. Do they mostly have radial plunging orbits into the galaxy, or do they have more circular orbits, or is there some mixture of the two? Another challenge is that masses that are reported in the literature are often reported within different radii. So they'll say, okay, I know the mass within 10 kiloparsecs, or I know the mass within 20. And so this plot on the right here is showing the mass, different mass estimates from the literature, and along the bottom is the distance from the center of the galaxy. And you can see that there's mass estimates from all sorts of different distances, and it's hard to compare them and figure out which models are more likely than others. Another issue is measurement uncertainties. These velocities and positions that we measure, they're not necessarily the true value. So you can imagine if we have some data point at the bottom that's the true value, and the yellow dots with error bars are what we measure, they might contain the true value, but we still don't know what the true value is. And finally, there's only 157 globular clusters, which is statistically is kind of a small sample. Okay, so we have all of these challenges. And during my PhD, I've been trying to overcome them. And for the first couple of papers that I put out, we did manage to cover a few of them. And I won't go through how we did that, but I will show you some of the results. So with the statistical method that we're using, we actually get a mass profile. So that's the gray regions that you're seeing on the plot on the left. And this mass profile is really useful because then you can read off what the mass estimate is and uncertainties in that mass estimate within any radius of the galaxy. So it makes it useful to compare to other studies. Okay, but in overcoming those challenges, we were actually only able to use 89 of the 157 globular clusters. So can we do better? And what about those measurement uncertainties? We'd really like to include those. And the answer to that, after talking with a statistician, was to use a hierarchical Bayesian model. So the basic idea of a hierarchical Bayesian model is that you have a model for how your measurements are made. And then you assume that the measurements that you made in the true underlying values of those properties come from some physical model that you're assuming. And the physical model includes your model for the galaxy and maybe a model for the globular cluster population. And then from that, you can also include constraints on the model parameters. Okay, so with this hierarchical Bayesian model, we're now including those measurement uncertainties, and we were able to increase the sample up to 143 globular clusters. And if you want to know why 14 aren't included, you can ask me after. Okay, so before, this was the mass the mass estimate that we had with 89 globular clusters and not including measurement uncertainties. And then this is the mass that we get when we do include uncertainties, and we're using 143. So they're actually pretty similar. I won't go too much into the discussion about this, but I think these results are encouraging, and the method in particular is encouraging. Like being able to incorporate these measurement uncertainties in a meaningful way is something that could have broad implications for other areas of astronomy as well, where measurements are always uncertain, and often we have incomplete measurements. And I think this is also important for a lot of future data that's going to come available, because there's a project called HST Promo where people are measuring more proper motions of these globular clusters, so that'll be really great. And there's also big data projects like Gaia, which are measuring the positions and velocities of millions, I think 1 billion stars in the galaxy. So with that, I'll just leave our mass estimate for the galaxy within 200 kiloparsecs and acknowledge my funding sources and my school, and thank you very much.
I'm Matt Malkan. I'm going to describe work done at UCLA with a brilliant graduate student, Daniel Cohen. Big problem that astronomers extremely interested in is understanding cosmic origins. But unfortunately, the youngest galaxies that we want to understand are terribly faint, and it's even worse than that because they start out in small little fragments, maybe 1,000th the size of the Milky Way, and they later merge and grow up. So if you even want to find those objects, let alone study them, we really need some very strong, distinctive emission that those galaxies would give us. And today, I'm going to say we got that break. Pass the first slide there, sorry. What I'm going to describe to you is the detection of the strongest single emission line that is emitted by young galaxies, which contains a rather shocking amount of the entire light of these galaxies. And contrary to expectations, it's not coming from hydrogen, it's coming from a particular kind of oxygen which has lost 2 electrons. I'll try to tell you why that's an interesting surprise. The background of this is deep fields, as a lot of cosmology is. You've seen deep fields. Here's a particular one called the Subaru deep field. That's about the size of the full moon there. And we've measured about 500,000 galaxies in that picture. I'd have to blow it up to show them all to you. It'd take a little bit of time. And what we're particularly looking for in this study was about 5,000 of them that are at a very high distance. So that's a big look back time when the universe was 11 billion years younger than today, just a few billion years after the Big Bang. In other words, the volume of the universe was 70 times smaller than it is today. So finding 5,000 of those is a nice thing, but it is not a big breakthrough. This kind of work has been done before. There they are, if you want to see where the 5,000 of them are. And they have some interesting clustering properties. The next step, though, we're getting a little bit more interested here, is to look at the same field with these same galaxies very deeply with infrared telescopes. On the ground, there's the Euclid and Mauna Kea, and in space with Spitzer, well, it was getting ready to go to space there. And so we looked very hard at this Subaru deep field with those telescopes. Didn't detect too many of those galaxies at all. But the advance here is if you can average the infrared signals from the 5,000 galaxies, so each one of them is very hardly marginally detected, add them all up to average it, and you can detect them very well, because we know where the galaxies are to look. And here's the big surprise. Doing this at many different infrared filters, there's one particular filter at one particular wavelength which was much too bright, more than a factor of 2 too bright compared to what it's supposed to be. That's the surprise, not expecting it. I'll show you, and here's the money plot. It's the only plot here of the data, and you can see optical data on the left there, infrared data on the right. This is an average, though, of 1,294 galaxies, which is why we're able to detect such a weak signal. These are very faint galaxies. And what I want you to notice is between the dashed lines, you see that one filter, it's at about 2 microns, is much higher than it's supposed to be. What I mean by it's supposed to be, it's much higher than all the other wavelengths which are coming from just starlight. And we have a nice model of what stars, young stars, are supposed to look like. That's described by the blue line there. And this is way above it. It's not coming from starlight, contrary to what we might have expected. It happens that this light, this is the hype of this, why I chose the color scheme for all the slides here. This is redshifted green light. It's a very distinctive, intense green light that these galaxies are just pouring out. Now, I'm going to be honest, it was actually known that a very small number of galaxies occasionally do produce, say, several percent of their energy just in this green light of oxygen before. The shock here is that if you go back in time to the younger universe, everybody's doing it. Not just 1 in a million galaxies, not just a few freaks. All galaxies started out this way. That was not expected at all. Just a quick little review of how a galaxy could look green, the whole galaxy. On the left is an example of what I was expecting from how intense star-forming galaxies look like today. You have a typical young hot star in the middle, shown by the blue circle. It's emitting ultraviolet photons, and they will smack into hydrogen atoms there, shown, and they have enough energy to kick off an electron. And so the hydrogen gives a very distinctive signature of a beautiful pink light. You can see it in a small telescope. Just look at the Orion Nebula, for example. There it is. And there are galaxies, many galaxies, where you see thousands of Orions, and the galaxy looks kind of pinkish. So I kind of expecting that that's what the first galaxies would look like, the youngest ones. Not the case at all. They're actually much brighter than that, but instead, I'm giving you a little bit of the explanation here of why we think they turn so green, is that the star on the right-hand side must be somehow much hotter, more energetic than even the hottest energetic stars that we're familiar with today. And so they're emitting not just UV photons, but extreme high-energy UV photons. They're practically X-rays coming out of these stars. And what can an X-ray do that the normal UV photons can't do? They are energetic enough to knock off 2 electrons from an oxygen atom. The first electron not too hard. Getting that second one away takes an awful lot of energy. Oxygen doesn't want to part with it. But then if you have doubly ionized oxygen, which apparently we have a lot of there, it gives a very distinctive, very strong glow at a particular wavelength in the green that you actually might know this. This process happens in a special locale in the Milky Way, right around the hottest stars known. There's just a few of these. These are called planetary nebulae. They're basically on their way to becoming a white dwarf. And these are a small little phenomenon, a small example of what might be going on in an entire galaxy through a different process. It's not through dying stars, it's through stars just being born that are outrageously hot. We're talking hotter than 50,000 degrees is what you need to do this. So really surprisingly high temperatures. So the discovery that this is a large emission from most galaxies when they're young, when they're forming, really opens up now a new field of study. This is how the next generation of space telescopes is going to first find the youngest galaxies at the highest distances and then tell us all about them. Give us all the information that we want about their dynamics, mergers, dark matter, chemical enrichment, and for just to name a few. And the nice thing about this is, because of the large redshift of these galaxies, you need telescopes optimized at the longest wavelengths, and that's exactly what we're getting here. Of course, everybody knows about JWST. We launched in 2018. There's also Euclid coming along a few years later, and WFIRST coming along after that. They are going to do a wonderful, brilliant job in studying the youngest galaxies, particularly in this strongest feature that we've got to look at. And this, of course, the younger the galaxies are, it's the more interesting, the closer back to the Big Bang, the closer back to the first generation of stars formed in these galaxies. I really should call them little fragments of galaxies that are eventually going to grow up. That's why I'm calling them dwarf galaxies, will be detected through this amazing oxygen plus emission. And so, since that one powerful probe can give us all of this information, sorry for the pun here, but I think a whole range of studies where we really can understand how galaxies are born is now green lighted. All right, sorry about it. I got to apologize about that. And that's my story.
Thanks very much. 5 very compelling presentations, which I appreciate. We will now turn to questions and answers. We'll start here in the room. Please wait for the microphone, and when you get it from Larry, identify yourself, your affiliation, and who your question's for. And you guys don't need to worry about your mics because they're controlled from the back. So I think we have Monica down here in the front.
Hi, I'm Monica Young with Sky and Telescope. My question is for Gwendolyn. I was wondering if you can just clarify for me the extent of the stellar halo and the dark matter halo, how the two compare. It sounded like you were saying the stellar halo was out to 200 kiloparsecs.
Oh.
But then also, let's see, I wanted to ask you also how your mass measurements compare to previous measures, because I think it's been a contested number, so.
Yeah, for sure. Thank you for those great questions. So the stellar halo definitely doesn't extend as far out as the dark matter halo. The dark matter halo is thought to go out at least to 300, 350, or maybe even further. Once you get to 350 kiloparsecs, then it may start overlapping with the Andromeda Galaxy's dark matter halo. So we don't want to extrapolate further than that because maybe there's some dynamics happening there. And the stellar halo, I know the globular cluster system goes out to about 125 kiloparsecs is our furthest globular cluster. And I think the stars don't go much further than that, but I don't know the exact number, so, yeah.
And the comparison?
Oh, right, sorry, I forgot about the second question. Yeah, so our mass results are definitely on the lower end from other studies. And so that would imply that the fraction of dark matter would be a bit lower. But I'm not saying that our results are any better or anything than anyone else's. I think that there's lots of improvement to be made with the models that we're using right now. We're assuming spherical symmetry, and we're making some assumptions. So yeah, there's lots of improvements that we need to make still.
Other questions here in the room? Over here, Calla.
Hi, Calla Cofield with Space.com. I have a question for Gwendolyn and then one for Matthew. I was just wondering if there are any other totally different techniques for measuring the mass of the Milky Way, maybe that don't involve globular clusters, and how you showed the comparison with globular cluster studies, but how does it compare with some different studies, and what are those?
Yeah, so thank you. I should first clarify that those are studies using different methods and different objects too. So some people will use dwarf galaxies as tracers of the dark matter halo, sometimes blue horizontal branch stars. So there's that method of using tracers, but there's also some other methods. For example, you can use something called the timing argument, which considers the Andromeda Galaxy and the Milky Way galaxy, and how long have they been interacting, and you can derive a dark matter mass from that interaction. So there are other methods as well, yeah.
And Matthew, is it surprising that there would be that much oxygen in early galaxies, and how do you maybe explain that?
It's a darn good question. Yeah, it is a little bit surprising, and we're going to have to study this better. I think the combination of studying the hydrogen pinkish emission and then the stronger green oxygen emission is the way to go. But what it's looking like, it's a little early to give you a definitive answer, is that almost as soon as the very first generation of stars was born, some very massive stars must have gone supernova almost immediately, scattering a small smattering, just a little bit of oxygen atoms throughout the gas in those galaxies, allowing us to see this green glow almost immediately. It looks like it's almost the first thing they did. It's like jumping off of an airplane and turning on your little green finder light. I don't know what color they actually are, but if they were green, it would be a perfect analogy there, so that astronomers can go find them and rescue them, except we're not going to rescue them. But right, so that's a lot of people thought, well, it's going to take a long time for stellar evolution to explode stars and make oxygen, and maybe we better just look for hydrogen first. But I don't think we'll get a jump on it with oxygen. If we can find a few, of course, that don't have any oxygen, then I guess those are the very, very first ones that haven't had their supernovas yet, in the first few million years, maybe.
Okay, Ethan?
Hi, this is Ethan Siegel with Starts with a Bang. This question is also for Matthew. Matthew, I'm less concerned about the oxygen as I am about the temperature. I think this is a big theoretical problem because even the most massive stars we see today, the only time we see this green glow is really due to newly formed white dwarfs and planetary nebula because they can reach these ultra-high temperatures. I think you need to get to about 50,000 Kelvin to make this doubly ionized oxygen. So can you comment on the theory for why these early stars, in these star-forming regions at these high redshift, why they might reach such high temperatures to generate these oxygen? Is it something due to lower metallicities or higher masses, or maybe is there a comparison to the most massive stars we see locally, like in the Tarantula Nebula?
It's a superb question. Come up and do the talk with me, actually. So this is a mystery. I kind of swept it under the rug. I gave a tentative idea that, gosh, somehow there are stars that are 50,000 degrees out there, contrary to what we've seen here. I mean, it really is not settled. But I like a lot of people worrying about this. I like a lot of the suggestions you mentioned. There must be something about the first generations of stars having so little heavy elements in them that a lot of extreme ultraviolet, high-energy photons manage to get out of their atmospheres without being absorbed. That might be something to do with it. There's some other more exotic speculations about having these stars rotate unusually rapidly or being in binary systems or things that I don't want to commit myself to which theory might be right. What I'm going to commit myself to is getting more and better data to try to nail down some of these possibilities. But whatever the possibility is, it's going to turn out to be a bit of a surprise because you don't hardly see these extreme high-energy photons leaking out from the hottest stars we've got today. You're exactly right. So that's why it was not predicted at all by anybody. Certainly having a strong preference for the most massive stars, that would help. Maybe only massive stars got formed first generation. Astronomers are very conservative. We want to stick with something we know, Orion Nebula, and just extrapolate that as far as it'll go. But if the evidence really pushes us, we're going to have to entertain more exotic. The universe may have been significantly different in how it formed stars early on. But we don't really know the answer to your question yet.
Thank you. Martin down in front. We're giving Larry his exercise.
Martin Radcliffe, freelance. First question for Gwendolyn. You alluded to for us to ask, why did you leave out some of the globular clusters? Was it related to what you were describing? They were being maybe influenced by external, influence from Andromeda, or
actually no. Those 14 globular clusters, they don't even have line of sight velocity measurements. So we don't have any information about how fast they're going. So all we have is their positions. So.
And a follow-up, if I may, to Eadie. Not because I was born near Durham, but you had a very interesting story. But I checked on the galaxy distance on the well-known, rather unreliable reference, Wikipedia.
I'll have to fix that.
And I wonder if you had information about your distance measurement, because it's quoted as 58 million light years, and you said 38, which is a lot closer. Mm-hmm. Do you have any information on that distance measurement?
Yes, so the distance was calculated by Golding and Alexander 2009 paper. It accounts for gravitational pull by the local group, the Shapley cluster, and all the other clusters close to us. So it's a more accurate distance than what you found in the Wikipedia. Yeah.
Yeah, we had a presentation a day or two ago about the NASA Extragalactic Database that has lots of all that stuff in it. A little more reliable than Wikipedia. Yeah.
That's right.
Any other questions in the room? Do we have any online? Okay, we'll let Inga relay some of those.
Okay. The first question is from Govert Chilling, freelance from the Netherlands. And the question is for John Debes. Would this tilted and precessing inner disk also leave some fingerprint in the ALMA data?
Yeah, that's a great question. So I would think yes. If it's being caused by a massive companion of about a Jupiter mass, that would create a gap in the disk. And that's why I picked 1AU, because that's where the ALMA data shows a strong gap in the millimeter where the biggest dust resides, and that's pretty much the only strong signature we see of something that's consistent with the period that we see. As we go, if you look at the ALMA data in detail, as you go out to 6AU, which is where the constraint from the period is, you don't see anything else that has such a large gap. So that's why we're picking 1AU as the most plausible location.
Thank
now,
you.
If I recall, that spectacular ALMA image that was on the front pages of newspapers was made before the array was complete. So is there a chance that when they go back with the full array, all the antennas at the maximum separation, that they might be able to get an even better image of those gaps and maybe push in farther to the area that you're looking at?
I think that's definitely possible. TW Hydra is definitely the best candidate for it because it's so close. So whatever the ultimate final highest resolution that ALMA can obtain, they're going to go back and try to probably answer those questions in more detail. That gap is just barely resolved at the moment. And so having higher resolution data from ALMA would really also help to characterize how wide that gap might be, how deep it is, and other questions like that.
Okay. The next question is also from Gobert Chilling, this time for Gwendolyn Eadie. Can't you also use the kinematics of halo stars to derive the Milky Way's mass profile?
Yes, you definitely could. And actually, that's something I've been thinking about because of the Gaia data. So the Gaia satellite is going to be measuring the positions and velocities of a billion stars in the Milky Way. So once that data becomes available, and we will have some proper motions in the years to come with that data, so that will be really exciting to be able to use that to get the mass, yeah.
Thank you. The third question is from Keith Cooper, freelance from the UK, a question for Matthew Malkan. Last summer, there was a study that suggested green galaxies were an intermediate stage in the evolution of galaxies from blue to red. Do your findings contradict that, or are they two different populations of green galaxies?
Thank you for clarifying this. Astronomer, we've got to be a little more careful with our terminology. They're completely different things. When astronomers in those papers that you refer to describe green galaxy, all they mean is they're just looking at the starlight of those galaxies, and really all galaxies look either kind of whitish or a little bit on the pink side if they have more old red giants, or a little bit on the bluish side if they're relatively younger galaxies. It was really, I'm sorry, I don't want to criticize anybody, it was probably an unfortunate shorthand to call galaxies that had kind of intermediate star populations, you know, like early type spirals. They got called green galaxies. They're not green or anything like that. They're kind of whitish. It's just an unfortunate term. These galaxies in the early universe are actually green. I mean, we have actually a few examples locally. You look at them, if you look at them in a big telescope, they actually would look green. There's so much light.
Peas?
Thank you very much. And in fact, the examples I can point you to are very rare examples found by citizen scientists in the Galaxy Zoo project. They noticed these green splotches, and they're called green peas now. Now, there's some really bad puns about give peas a chance and so on, but at least that is a more descriptive. Those really are green galaxies, and I think they're perhaps our closest local analogs to what the universe was doing all over the place in the early days. So thank you for clarifying that. So we have the real green galaxies, other the guys are not.
Thank you.
Yeah.
Anything else?
Purple, actually, he's right. Purple would be better.
All right.
Purple.
Any other questions in the room? Oh, goody, it's my turn. People who come to the press conferences know that I always have questions. Okay, so my question is for Peter and Eadie. Every time I hear anyone talk about active galaxies and supermassive black holes, they always say astronomers believe or think that every large galaxy has a supermassive black hole. So, in a sense, I'm asking if there's, what's the surprise here, or what is it about finding hidden accreting black holes that's giving us special insight into what's happening in the centers of galaxies. If we find a black hole, it's not that we didn't expect it, right? Because we expect there to be black holes. So what are you distinguishing between here? There's black holes that we see easily. There's black holes that are obscured. There's black holes that are quiet. There's black holes that are accreting. What is it that you're really driving at? And why is it so important to find these hidden examples?
So I guess to be able to see and study actively accreting supermassive black holes, it can tell you more about how they evolve and grow over cosmic time. It can tell you a lot more about, as well, the cosmic X-ray background, because the shape of the spectrum of the cosmic X-ray background more or less confirms that there should be a high population of heavily obscured active galactic nuclei. So with NuSTAR, we're able to start properly resolving these hidden active galactic nuclei for the first time, which can pinpoint more to the origin of the cosmic X-ray background. And,
okay. Did you want to add anything to that, Eadie?
Yeah, so as we know that every massive galaxy hosts supermassive black holes, and these supermassive black holes co-evolve with its host galaxy as we observed. And so we expect them to be more obscured in the higher redshifts than the lower redshifts. In fact, that's what we start to observe now. So this finding the sensors of obscuration of supermassive black holes can help us to understand the co-evolution between creating supermassive black holes and their galaxies across cosmic time, as what Peter said earlier. Yeah.
Okay, very good. I have a question for Gwendolyn and Eadie as well. Some of you will probably remember that this isn't the first time we've had a press conference that included a new mass for the Milky Way. In fact, after the last one, Stephen Colbert reacted because the announcement was made at a AAS meeting that the Milky Way was more massive than Andromeda, and so Stephen Colbert said, you know, go America's galaxy. Now you have brought the mass estimates down a bit relative to some of those earlier ones, and I'm wondering if I should try to get Stephen Colbert on the phone, or maybe ask Neil Tyson to do it for me, since he's got his number. How far should we take this? I mean, is this really an open question, or do you have any plans to try to do what you're doing now with the Milky Way with Andromeda so that you can compare apples to apples?
Actually, that's a really great question. So yeah, there's so many ways that this work can go, and going to look at other galaxies is definitely an option. And I think the method that we're using could be very useful there, because when you look at Andromeda and you look at its satellite population, we're never going to know the proper motions of those. We only know the line of sight velocities. So having this kind of method to use for Andromeda to get a mass for that galaxy could be useful. So that's something I want to do, and then it would be neat to compare the mass of Andromeda to Milky Way that way. Yeah.
Okay. I also just wanted to mention, since we've had a lot of parsecs and kiloparsecs in these briefings, and I just wanted to provide the quick conversion. A parsec is about 3¼ light years, so a kiloparsec is like 3,250 light years, in case you're trying to keep track. And all of my other questions. Oh yeah, I had one other question also for Gwen. When you showed the plot of your mass profile, there were an awful lot of points well out of your error bar range. And I'm just curious if you have any comments about why that is. I mean, why should these methods produce? Because a lot of those looked like they were consistent with each other, whereas yours are not consistent with those.
Yeah, so I think that one of the biggest differences was that I'm only using globular clusters and I'm not including dwarf galaxies. And a few of those studies include dwarf galaxies, which go to much further distances. And it's not always clear if those dwarf galaxies are bound to the Milky Way. So when I say bound, I mean like they're in closed orbits. They're not just passing by or doing some sort of like loop around the galaxy. And so in one of my first papers, we actually did include the dwarf galaxies, and we got a higher mass. We got 1.2 times 10 to the 12 solar masses. And that was assuming that these dwarf galaxies are bound. So I think the dwarf galaxies could play a large part in that, but then also the models that you're assuming as well. So, yeah.
Okay. Any other questions here? Anything else come in online? Okay, this is great. We've used up the hour just right on time. So I'd like to thank everybody. Thank you for your presentations. Thank you for your attention. We have one final press event. This afternoon at 2:15, there will be a seminar for science writers. No news per se, but a lot of background information on this year's biggest predictable astronomical spectacular, the August 21st total solar eclipse. So we hope to see you back here at 2:15. Thanks a lot. We're going to do a group photo. Can we just let me just